Imagine being able to see inside a human body without the need to cut or make any type of insertion. Fortunately, several types of non-invasive tools have helped doctors diagnose and treat patients for decades, like X-ray, ultrasound, and most recently, MRI, magnetic resonance imaging. MRI technology brought about a new era in medical imaging. It was a revolutionary new tool that could be used to generate a 3D image of the human body and clearly distinguish different tissues, not just solid masses like the X-ray. When such a new medical technology becomes available, many questions come to mind, like, how does it work? Is it effective? And most importantly, is it safe? The technology behind MRI is called nuclear magnetic resonance, NMR for short. In 1952, Hermann Karp produced the first one-dimensional NMR spectrum. What looks like random peaks on a backwards graph is actually a precise reading of the connectivity in a molecule, specifically acetic acid. To understand how he did this, we need to bring up several key concepts. All matter is made up of atoms, which consist of protons and neutrons at their center, or nucleus, and electrons orbiting the nucleus. The most common hydrogen atom consists of one proton and no neutrons in its nucleus, allowing us to refer to it simply as a proton. All protons have a spin number, the most basic quantum number that describes the direction of its electric field that is either +1/2 or -1/2. Wait, I don't get it! It's okay, don't worry about it for now. But if you really want to learn more, you can always sit in on a local quantum mechanics class. When exposed to a really strong magnetic field, the spin of these protons line up, and the negative spin becomes a relatively higher energy state, causing most protons to enter the positive spin state. When exposed to a specific radio frequency, the protons of a sample will absorb this energy and momentarily flip from the +1/2 state to the -1/2 state, after which they will relax back down to the +1/2 ground state, emitting the same frequency that they absorbed. Depending on the relative shielding experienced by each proton due to its neighboring atoms, each nucleus will require a different frequency of electromagnetic energy to bridge the energy gap between the spin states and flip the nucleus. Put together, these two concepts make up the principle of NMR and make it possible for us to determine the presence of groups of hydrogens based on the frequencies emitted after a wide range of short frequency pulses fired simultaneously at a sample. If we now look back at our original graph, each peak represents a group of hydrogens with the same connectivity. Their position along the bottom axis indicates the specific frequency they absorbed and emitted due to different levels of shielding from their surrounding atoms. Using this data, we can extrapolate the structure of an unknown organic molecule. Because almost all organic matter contains hydrogens, NMR can be used to determine their presence and structure. To recap, in a strong magnetic field, the protons in an organic molecule absorb a range of radio frequencies, flip their spins, and emit the frequency they absorbed. This is the process of NMR. Wow, that was dense. You probably forgot why you were watching this video. Stick with us a little more. We'll get to the point soon. So how does this all relate back to MRI? Well, now that we know how it works, we can begin to answer the second question: is it effective? Let us look at how accurate MRI technology really is. A physician may prescribe an MRI when he or she needs to take a closer look inside a patient's body to determine the cause of an illness or look for unusual tissue. The patient will often receive an injection of chelated gadolinium, a non-toxic contrast agent that greatly increases imaging potential, whose paramagnetic properties can also be studied in a graduate inorganic chemistry course. The patient is then placed on a movable arm of the MRI machine and must remain completely still for the scan to work properly. Once inside, the patient is exposed to a very strong magnetic field from the enormous circular magnets inside the MRI scanner, approximately 1.5 Tesla. As mentioned before, this lines up the spins of the nuclei in the patient's body. Once he or she is in place, a transceiver begins slowly moving across the area of the patient that needs to be imaged, emitting and receiving a range of radio frequency pulses from the nuclei inside the patient, as was described earlier. However, instead of acquiring data in only a straight line, as is done in NMR, the transceiver rotates 360 degrees around the patient and is able to create slices of the patient's body. These frequencies are then processed through a mathematical technique called Fourier transform into a black and white image. When enough of these slices are collected, they can be stacked to create a three-dimensional representation of the image section of the human body. Because the pulses target hydrogen nuclei, only parts of the body containing water, fats, proteins, and other organic compounds will be detected and show up as visible, white images, while bones and air pockets will appear dark. A CT, computed tomography, produces cross-sectional images similarly to an MRI, but uses X-rays to produce them. Because of this, CT scans are more useful for imaging bones and dense structures of the body, while MRI is much more effective at detecting soft tissue. Ultrasound may also be used to examine soft tissue, but it is limited to imaging tissue close to the surface of a patient because it cannot pass through bone, and its signal weakens as it passes deeper into the body. This leaves us to answer the final and most important question: is it safe? As we have seen, MRI is an incredibly useful technology for non-invasively imaging soft tissue. But what effects do the magnetic field and radio frequency pulses have on the human body? The short answer? None. Magnetic fields have absolutely no negative effects on the human body. Just check out this frog levitating in a 10 Tesla magnetic field. Whee! Nor do the radio frequency pulses, for they are not in the range on the electromagnetic spectrum that can harm human tissue. However, the only restriction imposed on MRI is the exclusion of imaging patients with surgically installed pacemakers or metal plates. Due to the very strong magnetic field, no metal objects are allowed within close proximity of an MRI machine. Just look what happens to this unfortunate metal canister that got too close. Aside from this precaution, receiving an MRI scan is completely harmless. Your body receives more radiation from the cell phone in your back pocket every day than from a full body scan. There are also pros and cons to the different types of imaging we've discussed. Both ultrasound and MRI have no negative effects because they do not use radiation, while CT scans use ionizing radiation in the form of X-rays, which can be harmful after long exposure. In fact, there is an advised cap for how many X-rays one can receive in a lifetime. However, CT scans are faster than MRIs, lasting only 20 minutes compared to the MRI's hour. To recap, we have just investigated NMR and how it works to safely produce MRI images. In a strong magnetic field, the protons in the human body absorb a range of radio frequencies, flip their spins, and emit the frequency they absorbed. The information gathered from these emissions is then used to construct cross-sectional images of the body through Fourier transform and provide physicians with valuable insight into their patient's condition. Thank you for watching this video. Go amaze your radiology technician if you find yourself getting an MRI. I would also like to thank the Bridging Disciplines program at the University of Texas at Austin for supporting this project, and my amazing mentors, Dean Brett Iverson of the School of Undergraduate Studies and Dr. Jeff Marcelet of the Moody College of Communication, for helping me make this video.